Hello and welcome to my lesson today. My name is Mr. Johnson and I am going to teach Key Stage 3 physics, specifically with sound. For this lesson you will need a pen, a paper, just to take notes, a pencil if you want to copy any diagrams down. I'm just going to share my screen with you. Okay. So by the end of this lesson, what you should be able to do is describe key concepts of frequency, intensity and amplitude when talking about sounds. Describe and explain, using the particle model, how sound travels through different substances and which substance it travels through best. And describe other uses for sound than communication and speech, with some examples given. Let's take a look at our first one. Uses of sound. Sounds are all around us. We use sounds to communicate, to warn others of danger, and even just for enjoyment when we make music or we listen to it. Animals also use sounds, and they use them for some of the same things that we do, such as communication, to warn others of danger. But they also use it to stop others entering their territory, which again comes under communication. They use it to win a mate, to hunt. And in specialised circumstances, some animals can use it to find their way around or to hunt when they cannot see due to poor light conditions. So the question is, what is a sound? Well, sound's a way of transferring energy. Sound is a form of energy, and the energy is transferred. Sounds are made when things vibrate. What we've got on the picture here is a diagram of a speaker, and underneath is a sound wave, which we'll talk about a little bit more later. But you can see how the particles of air in front of the speaker here are being forced to vibrate backwards and forwards. An example of this would be the vibration of a tuning fork. If you strike the tuning fork against a hard surface, the prongs quickly vibrate back and forth. This makes a sound that we can hear by vibrating the air between the two prongs, the air particles in between here. The sound travels out from the fork as a sound wave, which carries the sound energy outward. So to understand sound, we have to understand what's carrying on the sound wave. And to do that, we need to understand a little bit about the terminology or the words that we use to describe waves. Waves have particular properties that we do need to know about. A wave has the highest point, as labelled here with the arrow, called a crest. It also has a low point, and this lowest point is called a trough. Every low point is a trough, every high point is a crest. The distance between two crests, or two troughs, is one complete wave. We call this the wavelength because it is the length between the same point from one wave to the next. In other words, one full wave from beginning to end. The height of a wave from its resting point, which is the purple line on the diagram, is called the amplitude. And the amplitude is something that we'll talk about in a short while with relation to sound particularly. But basically the amplitude is also the intensity or the volume of the sound wave. So, getting back to the amplitude idea, the amplitude of a sound wave is how far particles move as the vibrations pass through them. If we have a high amplitude sound and a low amplitude sound, you can see that the wave is actually different. The high amplitude loud sound has a higher crest or a lower, deeper trough from the resting position than the quieter sound. And again, this is because the particles that are vibrating are not moving as far. The larger the amplitude, the greater the movement and the louder the sound. We say that the sound is high intensity or high volume. The lower the amplitude, The smaller the movement, and the quieter the sound. We say that the sound is low intensity or low volume. Something else about sound waves, what we use to describe, is the pitch. Now, you might have heard of high and low pitch. You might even have tried to make a high and a low pitch noise. High pitch can be described as something close to the tweeting of a bird, whereas low pitch might be something like a whale song or the roar of a lion. Pitch is linked to something called the frequency of the wave. The frequency is the number of waves that pass a particular point every second, and it has its own unit, the hertz or Hz. The lower the pitch, the lower the frequency. That means that for low pitch sounds, there are fewer or less waves passing every second. This sound wave appears spread out on a diagram with each peak and trough further apart. If I wanted to do a lower frequency or lower pitched sound than this, then it would look something like this, where the sound wave is spread out even more with a much bigger distance between the two waves, meaning that less waves are passing in the same time. The higher the pitch, the higher the frequency. This means that there are more waves passing every second. The sound wave appears kind of bunched up, almost like you've scrunched up a slinky close together, and each peak and trough gets closer together. So with the example that we've got here, if I wanted a higher pitch than the one that's on screen, then I would be looking at something that does this, where there are more waves in the same amount of time, and those waves are closer together and more bunched up, with much smaller space between each trough or each crest. So, picture here, sound waves spread out from a source in all three directions. They don't just spread in a straight line from you to whatever you're talking to. As you're speaking to your friends, or as I'm speaking to the screen in front of me now, sound waves also spreading out from my voice, or from my vocal cords, in all directions around me. This means that as you get further from the source, the energy carried by the sound wave is spread out further to the surroundings. Now that might sound a bit awkward, but it means there's less energy for your ear to detect when you're further away from the source of a sound, because it's not just coming at you, but it's spreading out in every direction. And this is why the intensity of a sound seems less, or the sound is quieter, or too faint in some cases to hear, as you increase the distance between you and the noise. It's why people living far away from an airplane, or even people who are watching an airplane fly past in the sky, can hear a very quiet drone from the engine, but someone who lives near the airport probably has to wear earplugs whenever one takes off or lands. That's our first outcome. Describe the key concepts of frequency, intensity, and amplitude when talking about sounds. Our next outcome is describe and explain, using the particle model, how sounds travel through different substances. Here we go. So a quick recap, particle diagrams. Now you would have encountered these probably in year 7 and year 8 science. Particle diagrams tell us the arrangement of particles in the three states of matter. All three of them are present on the left. The first one is the gas, and you can see the particles are spaced quite far apart, and the little lines around the sides of them is meant to imply that they are moving quite quickly in random directions all around that box. Liquid particles quite close together, random arrangement, but they can move around each other, although they can't move apart from each other. And then the third box is solid. The solid particles are in what we call a regular arrangement. They're not random, they're lined up in rows, a bit like pupils going outside for a fire drill lined up by class and form. Those particles cannot move, and they can't move around each other, but what they can do is vibrate in fixed positions. Why is this important then? Because it's all linked to how sound travels. I'm going to play this for you. It's a 20-second clip. Just pay attention to the screen.
When an object vibrates, it pushes the surrounding air molecules into one another, starting a chain reaction of collisions through the air. These collisions travel in waves. When they strike your eardrum, it vibrates. This vibration is converted into electrical signals that your brain recognizes as sound.
So what we've got there then is the idea that whenever a vibration is set up in a material, that vibration is passed by vibrating particles to another material, such as the membrane in your eardrum, which also vibrates, and that is translated into sound. So sound is a traveling vibration caused by something vibrating, and it vibrates through a medium. All substances are made from particles. A vibrating loudspeaker makes the air particles close to the cone of the speaker move backward and forward when it's switched on and it is vibrating in time to a music or a bit of speech. So as that's vibrating, the particles themselves that are in front of the cone move backward and they move forward in the air. The sequence of moving vibrations form the sound wave. Now, in some places in the wave, air particles are squashed closer together. That's because some are moving forward as some are moving back. And where they're squashed together, these places have a higher pressure. In other parts of the wave, air particles are further apart. That's where one line of particles has just hit another line and they're bouncing away from each other. So they're spreading out. These places have a lower pressure. Sound waves, then, are also called pressure waves because there is a repeating pattern of high and low pressure areas throughout the wave. In fact, it looks a little bit like this, where the loudspeaker went off, the air particles in front of it are normally spaced and randomly arranged. But when the loudspeaker's on, every time the loudspeaker cone vibrates forward, it pushes or vibrates the particles in front of it forward. They hit the ones in front of them, bring them closer together. Then they bounce off backward whilst the other ones move forward. And we get this high and low pressure forming. So here we've got an area where the particles have been squashed close together. And just behind it here, where they're moving apart from each other, so that these ones can squash close together, and so on and so forth. And this will continue until the loudspeaker is turned off or the vibration is stopped. So which state of matter does sound travel fastest through? Well, sound needs a substance through which to travel because it travels by making particles vibrate. It has to have something. 3 states, solid, liquids, and gas. Sound waves travel fastest through solids. The particles in a solid are closer together than those in a gas, and they're more tightly bound than those in a liquid. This means that it's very easy for the vibrations to be passed on from particle to particle, and sound travels much faster. Let's just compare all 3 again. In a gas, the particles are very far apart. Because they're far apart, they can move easily in all directions, and they don't often bump into each other. This then means that if I vibrate one gas particle, I've got to wait for it to make its way across to its neighbour and hit that one to make that one vibrate the same way. This means that sound travels slowest in gases, although it does travel. Otherwise, whilst I'm talking to you now, because of the air between me and the speaker on my microphone on my computer, you wouldn't be able to hear me. In a liquid, the particles are closer together than those in the gas. They can move around each other. Sound vibrations pass through slower than in solids, though, because the particles are further apart than solids, and they don't bump into each other very often. They can slide around each other. But it does travel faster than in a gas. This is the reason why if you've ever been to the swimming baths and you're listening to your mates talk and then you put your head under the water, it suddenly sounds different. It's almost like the sound is higher pitched, and that's because it's moving faster because the vibrations are being passed quicker through the water. Finally then, the solid. In a solid, the particles are very close together and they're held together with strong bonds. Sound passes very quickly through solids because the particles are close to each other. This means they can bump into each other more often than in a liquid or in a gas. This means it's very, very easy for vibrations to be passed on. Sound cannot travel through a vacuum. There are no particles present in a vacuum, and as sound needs particles to vibrate to pass from point A to point B in space, then a vacuum is not going to work because there's nothing to pass on those vibrations. In fact, it's one of the famous taglines for a really, really old horror movie, Alien, in space, no one can hear you scream. And it's rooted in the science because space is a vacuum, so no one could hear you because you couldn't make a sound. And that's our second learning outcome, describe and explain, using the particle model, how sound travels through different substances. Our final one then, describe other uses for sound than communication and speech, with some examples. Uses of sound, example 1. You can see jewelry in a container, what looks like a deep fat fryer, I suppose, but actually this is an ultrasonic cleaner. The energy transferred by high frequency or ultrasound waves can be used to treat injuries, but it can also be used to clean delicate objects like jewelry. The object that is being cleaned, in this case the gold jewelry and the silver jewelry that's been placed in the basket, is placed in the basket and that's placed into a liquid inside the bowl. Ultrasound waves are sent through the liquid and they make lots of tiny bubbles. And I'm not just talking tiny like tiny bubbles you might see in your washing up bowl, liquid bowl, but teeny tiny bubbles. Those tiny bubbles get in between all the different cracks and crevices of the jewelry and they burst. And when they burst, they loosen the dirt and that then washes off into the liquid, leaving your jewelry sparkling and clean. Another example, which we did mention earlier on in the lesson, is using echoes. Here's an example of a bat using echoes with sound waves emanating out from the bat in red. And then where the sound waves have hit the moth in front of it, they've returned back in green. A reflected sound is called an echo. Animals like dolphins and bats can use echolocation to find their way around and to hunt for prey. The first thing that they do is they produce a burst of ultrasound, very high frequency sound. That then travels out and it's reflected off any object or any prey animal in front of them. When it's reflected, it takes time to travel back from the object to the bat. And they can detect how far away the object or the prey animal, the moth in this case, is just by measuring the time it takes from them emitting the sound to the time it's returned to them. They don't sit there with a calculator and work it out. They do it automatically. It's instinct. But they know where it is and how far away it is from that echo. They can also use this to sense the direction of the object, even in low light conditions. So not only does it give them an idea of how far away it is, but it also tells them where it is because of how the echo is reflected back to them. Using echo example 3, and this is a human use. Again, a reflected sound is called an echo. But humans can use sonar, and sonar is a set of equipment that uses sound, and we can use it to find fish in the sea for fishing fleets, or we can use it to investigate the depth of the sea if we are, for example, mapping the seafloor and want to know where the deepest part of the sea is. Warships can also use this to detect enemy submarines. The way that it works is they have a sonar set up with a speaker, and that burst of ultrasound is emanated from the speaker into the water. The waves are reflected off any object, or if they're investigating the depth of the sea, the seabed. They detect how far away the seabed is from the time it takes the echo to return. But unlike bats, we have to use an equation, and we use the equation speed equals distance divided by the time. Well, in this case, we divide the time by 2 because it takes half the time to get down as it does to come up if we're looking for the depth. And then we use that to calculate the depth of the sea, or the depth of a shoal of fish, or the depth of an enemy submarine. And here's the diagram of it. The ship sending out the pulse of ultrasound in step 1, the ultrasound reflected by the seabed in step 2, and in step 3, it's detected by the sonar equipment, whereby the equation speed equals distance and time divided by time is used. That's our final outcome. Describe other uses for sound than communication and speech with examples. And that's the end of my lesson today. I would like to thank you for watching. I hope you've enjoyed it, and I hope to see you again soon for another lesson. Take care.